Hi, and welcome to Lesson 1.5, Postulates for Points and Lines in Euclidean Geometry. So, basically, the fundamentals of this whole lesson come down to two different words. One word is postulates, and the second word is theorems. And postulates and theorems are going to be two of the biggest foundational pieces of the rest of your geometry life. So, postulates, we kind of can simplify the definition to mathematical assumptions. In other words, they're rules that we know are true without having to prove them. So, a lot of times, postulates will include the usage of any of those three undefined terms that we used or looked at earlier. So, our ideas of point, line, and plane. So, postulates are assumptions or rules that we know are true in mathematics without proving them. So, in other words, postulates are things that were chosen by mathematicians based on properties and other pieces. Theorems are statements that follow from postulates, definitions, and other proved statements. So theorems are based on postulates, definitions, or other proved statements. So in other words, while postulates are chosen, theorems have to be proven and supported by proof. And then just the brief note added in there. The Elements, or Elements, was a Greek book, actually a series of books, and they were created by Euclid. And Euclid, again, Euclidean geometry, named after Euclid. Euclid was a Greek mathematician who comprised this book of theorems and postulates, which it's one of the earliest recorded books that organized mathematics into theorems and postulates, and this occurred around 300 BCE in ancient Greece. So again, a lot of our mathematics and geometry can be traced back to the Greeks and Romans, geometry, especially the Greeks. Then we're going to look at the point line plane postulate. So the point line plane postulate can be broken down into three assumptions. Assumption A is the unique line assumption. And the unique line assumption states that through any 2 points, there is exactly one line. And if the 2 points are in a plane, then the line containing them is also in the plane. So through any 2 points, there's exactly one line. And if those 2 points are in the same plane, then that line is in that plane as well. The next assumption that's part of the point line plane postulate is the number line assumption. And the number line assumption is that every line is a set of points that can be put into one-to-one correspondence with real numbers, with any point on it corresponding to 0 and any other point corresponding to 1. So basically, in simple terms, what that means is any line can be turned into a number line with one-to-one correspondence to real numbers. And then our third piece is the dimension assumption. And the dimension assumption can be broken into three substatements. The first says that there are at least 2 points in space. The next, given a line in a plane, there is at least 1 point in the plane that is not on the line. So if we have a line in a plane, there has to be at least 1 point in the plane that is not on the line. And then for 3, it says, given a plane in space, there is at least one point in space that is not on the plane. So basically, in order for space to exist, there has to be at least 2 points in space. Then, given a line in a plane, there's at least one point in that plane that's not on a line. So in that plane, there's one point that exists outside of that line. And then given a plane in space, there is at least one point in that space that's not in the plane. So these 3 subpieces, A, B, and C, these 3 assumptions make up the point-line plane postulate. And these we all take as rules that are true without having to prove them. Then just a simple side note, naming a line. So when we are naming a line in geometry, so for example, any 2 points on the line can be used to name it. So if this line has points A and B on it, I could call this line AB or BA. If I put a point C on this line, I could also call it AC or BC, CB, CA. So you can use any 2 points on the line. Order does not matter underneath the line symbol. So this would be line AB or line BA. Also, if provided, there's typically by the line near one of the arrows a lowercase cursive letter. You can also name a line using that lowercase cursive letter. So this could also be named as line L or simply the lowercase l standing for line L. Then we have the line intersection theorem. So this is supported by proof. And the line intersection theorem says 2 different lines intersect at most at one point. So that means there could be no intersection, or at most 2 lines intersect, 2 different lines intersect at one point. If they intersect at multiple points, they would be the same line. So intersecting at one point for 2 different lines. So example 1 says find the coordinates of the intersection of 2 lines whose equations are given in standard form 3x minus 4y equals negative 17 and 5x plus 6y equals a negative 3. So when we are given 2 different equations in standard form, there's a couple options, but the easiest typically is to take the algebraic approach of solving for one of your variables. And again, this is going to be in this part first. So what you want to do is you look at your 2 equations and decide what you can multiply them each by to cancel out one of your variables. So I want to cancel the y's. So I want to multiply the top by 3, giving me a negative 12y, and the whole bottom equation will get multiplied by 2 to give me a positive 12y. We could also choose to cancel the x's. We could have multiplied the top by a negative 5 and the bottom by a positive 3 and canceled that way as well. But I chose to cancel the y's. So you'll see the first thing I did was multiply every part of the top by 3, every part of the bottom equation by 2, in order to allow me to cancel the y's. So then on top, I have 9x minus 12y equals negative 51. And on bottom, 10x plus 12y equals negative 6. So we can add top and bottom, solving a system of equations. That cancels out the negative 12y and positive 12y. So I'm left with 19x equals a negative 57. Then divide by 19, and x equals a negative 3. So once you've solved for one of the variables, Then you substitute that in to one of the original equations to solve for the other variable. So I chose to substitute in to the equation 3x minus 4y equals negative 17. So I'm substituting in the negative 3 for x. So 3 times a negative 3 minus 4y equals negative 17. Negative 9 minus 4y equals negative 17. Add the 9 to each side. Negative 4y equals negative 8. Divide both sides by negative 4. And y equals a positive 2. So that gives me the x and y coordinates. So I know these two lines intersect at the coordinate negative 3, 2. So the point negative 3, 2 is where those two lines intersect. Now, example 2 shows another way that we can solve this if they're given to us in slope-intercept form. So in this case, they say find the coordinates of the intersection of two lines whose equations are y equals 3x minus 7 and y equals a negative 2x plus 13. So because they're both in slope-intercept form, that tells me I want to graph them. And from graphing both lines, we can find the intersection. So right here, I graph the negative 2x plus 13 and the positive 3x minus 7 as my two different lines. So then what I did, starting at the negative 7, slope is a positive 3, so up 3, right 1, up 3, right 1, gives me my line. And then negative 2x plus 13, so my y-intercept's a positive 13, slope's a negative 2, so down to right 1, down to right 1, connect, and we have our two lines. They intersect or appear to intersect at 4, 5. So at the coordinates 4, 5. So then once we've found where they appear to intersect, we can always check the xy coordinate in the equation. So we could plug that in to either of the equations and check. So 4, 5, plug that into the first equation, substitute the 5 for y, the 4 for x, and we end up with 5 equals 3 times 4 minus 7. 5 equals 12 minus 7, so 5 equals 5. And then substitute it into the second equation to check to make sure it works in both. And again, substitute the 5 for y, 4 for x. End up with 5 equals negative 8 plus 13. So 5 equals 5. So both are true. So that definitely is the point where they intersect. And then our last piece for today's notes is the idea of parallel lines. So parallel lines are two coplanar lines that have no points in common. So the first thing with parallel lines, again, they have to be on the same plane. If they're not on the same plane, so if they're not coplanar, then we would not consider them to be standard parallel lines. So on the same plane, they have absolutely no points in common, so they never intersect, and they're not the same line, meaning they have no points in common. So then example 3 simply says in the coordinate plane, are these lines parallel? So they gave us the lines in slope-intercept form. If they were given in standard form, what I would simply do is rearrange them into slope-intercept form. Then what we want to check are parallel lines have the same slope but different y-intercepts. So if your equations end up in slope-intercept form and have the same slope, both of these have a slope of 1 and different y-intercepts, positive 2 and positive 4, then they are parallel lines. So going back to our main idea though for today, and the main piece that we'll be building off of, the idea of postulates and theorems, and then our first postulate, the point line plane postulate, and then the idea of line intersections with the line intersection theorem.